Hi everyone, my name is Thoravi Kumaravel. Today I will be presenting DreamStream, a work that I did during my internship at Microsoft Research with Andy Wilson. I'm currently a PhD candidate at UC Berkeley, where I'm advised by Professor Bjorn Hartmann. Today, people spectate VR experiences through 2D videos, but this is known to have certain issues. With DreamStream, one can spectate a VR experience in VR, in 3D, as if they were there alongside the VR player. They can move around in the scene and take different perspectives. Brighter portions here are the parts of the scene that the VR player sees. In addition to seeing, they can also laser point to different elements in the VR scene. From the perspective of the VR player, they see the spectator, represented here by the green avatar, and the actions they do, as if they are part of the VR scene itself. They can see the spectator moving around and can follow the spectator. DreamStream can work over existing VR applications without access to source code. We have tested DreamStream with Beat Saber, Tilt Brush, Waltz of Wizard, Skyrim VR, Fallout 4 VR, and Blocks. But why do we need these capabilities? To answer that, let's look at VR experiences of today. They are amazing. One can do so many things in VR. Design and art, gaming, 3D modeling, education, socializing. VR provides a compelling experience for these because VR players feel immersed in the 3D and virtual environment. This is because VR players have increased awareness of the spatial structure of the virtual scene. They are better aware of answers to questions like where am I, what's around me. They can also view the scene in 3D because VR is a stereo display. Due to this, they are better aware of the scale of the scene. They feel how big objects are, how far they are. Also, VR provides them an easy way to carry out spatial navigation in a natural manner in the virtual world. But what about those who are watching the VR player do things? Now that is not so interesting. This is because spectators have neither of the advantages that the VR player had. They are just watching a 2D video. It is no longer immersive or interactive. In fact, it's no more interesting than watching a video of a non-VR application like those of 2D games. So our initial statement on VR experiences need to be revised. VR experiences today are indeed amazing, but only so for the VR player. In fact, watching VR experiences can actually be worse when compared to non-VR applications. VR feeds are often first person, so the more immersed a VR player feels, the more they look and move around. This makes the video feed shaky. People who view these 2D video feeds often lose a sense of direction in the scene, especially when the VR user moves around a lot. It also increases the disconnect between the two. What is impressive and immersive for a VR user need not be so for the viewer. The viewers then could fail to empathize with the emotions of the VR user. And finally, even if the spectator has a VR headset, they still have to watch the vanilla 2D video of the VR activity. This may be disappointing and underwhelming for a spectator. Closely related prior works include those in the domain of collaboration in VR and live streaming in VR. These systems provide valuable insight and novel interaction patterns for developing VR experiences where multi-user interactions are a core aspect of the experience. However, these features must be built into these systems during the development of the VR application. This is similar to how multiplayer games are developed today. In contrast to such multiplayer approaches, the focus of DreamStream is to bring such interactions and features to applications that were designed to be single user. Another set of related prior work is general purpose media sharing systems that can retrofit over existing systems for the purpose of collaborating over and sharing 3D media. First of these is the work by Nidra et al. That allows 3D reconstruction of OpenGL scenes. It is an inspiring idea, but it makes specific assumptions on how the geometry information is stored, culled, and the nature of the architectural scenes. These assumptions do not hold true for today's VR applications. Tutoriver allows sharing of VR activity to others in an application agnostic manner, but it is not meant for live interaction scenarios. The two most closely related works to DreamStream are Reality Check and Transceiver. Both of these works propose ways to extract depth from existing VR applications as well as to composite graphical elements into it. In our work, we build on the technique proposed by Reality Check and modify it to suit our needs. Transceiver aims to mitigate issues in asymmetric communication between a spectator and a VR player. While this may be sufficient if the goal of interaction is a focused collaboration, it may not enhance the spectating experience of a spectator, because the output is still a 2D video feed. In our user study, we use transceiver as the baseline condition for comparison with DreamStream. We'll talk about it later. So how do we first go about building systems for spectating VR activities? Today, there exist three approaches. First is the multiplayer approach. In this, the player and the spectators each have a local copy of the application assets. For the spectators, the player experience is recreated by transmitting data such as player and object poses and events. Most multiplayer games today use this approach, and hence the name. This allows every spectator to see the app in 3D and interact with it. However, every spectator has to own a local copy of the application. The app can be huge and might not be supported in the spectator's hardware. Furthermore, these apps need to be built ground up to support collaboration. With the streaming approach, the application is hosted only on the VR player's computer. A 2D video feed of the player's activity is then streamed to the spectators. This approach retrofits over existing applications. The spectator also does not need to have a copy of the application. However, the spectator is typically not in a 3D immersive environment and has no interactivity. An emerging approach is the cloud approach, where the application and assets are stored in the cloud. All the interaction data is sent to the cloud, and the cloud in turn can render a separate video for each person connected to it. While the 3D data is not transmitted, it's possible to have 3D interactions if the latency between the cloud and the spectators is less. However, just like multiplayer approach, the apps need to be designed ground up to support this. In our work, we introduce a new approach that adopts many of the features and technology of streaming, but also allows spectators and players to have experiences and interactions that are typical of the multiplayer approach. The main idea is to embed with the streamed video the corresponding depth buffer that was used in the rendering process. These depth buffers are commonly generated in today's 3D graphic rendering pipelines. It captures much of the 3D information of the scene from the player's viewpoint. Unfortunately, it misses out on any occluded information, which is a limitation of this approach. Now there are three main components to DreamStream. First is the DreamStream host that runs on the VR player's PC and handles all the depth and video data capture, encoding and transmission. Next is the DreamStream relay that can run on the same or different PC. This handles the buffering and distribution of 2.5D frames as well as exchange of other application data. Finally, the DreamStream client that gets updated application data and the encoded textures from the relay. It decodes the textures, performs 3D reconstruction, and renders it into a VR or 2D UI to the spectators. DreamStream's 3D reconstruction has three parts. First is the 3D reconstruction of the VR scene as captured from the first-person view of the VR player. Second is the 3D reconstruction of the VR scene as captured from a third-person perspective that is controlled by the spectator. And finally, a Kinect-based 3D reconstruction of the body of the VR player, composited at the right place in the VR scene. The spectators and the VR player are also rendered as virtual avatars in the scene. To achieve this, DreamStream uses two concurrent 2.5D streams, a primary 2.5D stream that is captured from the first-person view of the player, a secondary stream that is captured from the third-person view that is controlled by the spectator. The streams are updated at different rates and appropriate transforms are applied to the depth data to reduce the reconstruction noise. These are explained at a greater detail in the paper. Reconstructions from the two streams are combined to produce a single 3D stream that the spectators can view in VR. Besides viewing in VR, the spectators can also use an interactive 2D viewer of DreamStream to view the live stream. More details on the interfaces can be found in the paper. We compared DreamStream with Transceiver, and with DreamStream, our spectators found it easier to communicate to, refer to objects, and spatially guide the VR player. With DreamStream, they also found it easier to explore and understand the VR scene, and felt that spectating was more enjoyable, immersive, and co-present with the VR player. Finally, they perceived a lesser workload when using DreamStream. I'm stopping here in interest of time. For more details on evaluation and limitations of the work, please refer to our full paper. Thank you.